in the planetarium community working towards transitioning to the field of the big data era. He has produced, written, and directed full-dome planetarium shows, stereoscopic films, and special format media, which have received both critical and popular acclaim. His scientific visualizations have been widely viewed in film, television, and print, and he has decades of experience as an astronomy researcher. So welcome to Mark Subarau.
Thank you. Thank you, Juana. And is my mic here? Yeah.
Alejo. Alejo. Alejo el micrófono.
Okay. All right. Well, thank you very much, Juana. I'm so happy to be here in Colombia, and I'd like to thank the organizers for this opportunity. It's really great to be here. This long title for my talk is trying to represent a sort of notional idea, this idea that we're at a transformative time in what we can accomplish in astronomy communication, in science communication, because of these elements that are coming together, because of the data rich, the free data that's available, the open data, because of the technology we have to get that data out to the public. I think it can lead to a new way and a more powerful way to communicate to the public and communicate in a way that expands what we can do, that elevates the level of that conversation, that allows us to talk about things closer to the cutting edge. So that's my goal. That's what I've been working towards. First, let me tell you a little bit about me. I've been working kind of with my feet in two worlds and moving back and forth between life as a research astronomer and an outreach scientist. And for many years, actually, with split jobs and split institutions going back and forth. And as I've been getting older, I found that life is very tiring. So what I've been doing lately is actually working in a way to try to bring these two communities closer together. So some of that work involves work with the planetarium community, working on the way that community deals with data, deals with scientific information, and try to do so in a way that's analogous to the sort of way that cutting-edge astronomers handle data, right? So we're trying to move the outreach community closer to the research community. I'm not going to talk, I'll show you some results of that. I'm not going to talk about the details, but at the end, I've got stuff on GitHub, and I'm very happy to share that with you. And the other aspect is trying to get scientists more involved in outreach and trying to make that outreach that they do as impactful as possible. And we'll talk a lot about that. So if I go back 18 years, and I can remember it's 18 years because I took this new job right when my son was born, and next week is his 18th birthday. I started working on the Sloan Digital Sky Survey, and my job on that survey was to write the software that would calculate the redshifts of galaxies. And from redshift, you get distance, and you build up this map of the universe. And we were building what would be the largest map ever made. And I started working on it for years before we had any data. Then we started to get a little bit of data, and then it started to come faster and faster. And we ran into a problem. And that problem had to do with the fact that before, it was hard to take a redshift. It took a long time. And so you couldn't look at the whole sky. And people would look at, just in one direction, or they look at a thin strip. And what you had is a 2D map. Like we have 2D maps of the Earth. And if I want to show you a 2D map, I can just plot it. And this is the famous stick figure diagram that was showing the first hints of large-scale structure. We were getting the first large three-dimensional map. And there was no good way to look at that. So I got interested in computer graphics, initially working at a space actually like this, actually better than this one, but I couldn't find a good picture. So this is a cave. I was working at the one at Argonne National Lab, and we would take the data into this projection room where you project on 10 foot by 10 foot, 3 meter by 3 meter walls in 3D, completely surrounded by the data, and you could fly around. It was an incredible immersive virtual reality experience. It is actually superior to the commercial virtual reality that's coming out today. It was just way more expensive. So this was an incredible experience, and it gave me a sense of the power of visual exploration. The idea that while I had been involved with my PhD in studying the properties of galaxies statistically, that didn't convey the whole story. There was a visual understanding that in many ways was much deeper and not really well appreciated by research astronomers. I'll let this play for a little while I continue to tell a different story. But that led to this idea that I was having in my hands, as more and more data came in, a picture of the universe that was more complete than anyone had. And we could see this on the computer screen. I started to teach myself computer graphics. We had some video game-like experiences. But I felt that I wanted to share that with the public. And actually, I didn't mean to show that video. Hold on. I'm going to go back. I meant to show this video. Actually, can you click on that for me? I apologize. Nope, it ain't working for you. We will skip that video. You can get it online. Anyway, we're going to fly through the universe. And that's led me to where I am today, where we're trying to take this information and share with the public. So this is a space I direct, which is called the Space Visualization Laboratory. And here we have lots of tools and different ways of visualizing the universe, different ways of interacting with that data. And we use that to carry out conversations with the public. We don't give lectures. We have one-on-one dialogues, augmented by a wealth of visual resources. This place is consistently evolving. This is from a few years ago. But what I wanted to get to is something more like this. So this is the vision. This is where I want to be. A very seamless, natural way to interact with data in a way that lets you tell a story. Here I'm navigating to my home world. All right. So, things are starting to change in astronomy. What does it mean to be in that big data era? This is kind of a sexy word, an often misused word. In some sense, it's not just that there's lots of data. It's that what we can do with that data is changing. How we can access it, how open it is, and astronomy benefits from having the most open data of any community, any scientific community, or really any community. But also how we can communicate that. And certainly the approach that I'm very interested in is how we can use visual tools to communicate that big data. So we're entering that era. Over-clicking again. And the sort of vanguard of the big data era is LSST, the Large Synoptic Survey Telescope. So, the beginning of next century, this beast is going to come online, and it's going to change how we observe the universe. We're going to go from taking pictures of the sky to taking movies of the sky. And if anybody if you go to your computer, it takes, I can store a lot of pictures with the same amount of space I can store a movie. So we're talking about 100 petabytes of data over the history of the survey, 30 terabytes of data every night. It's going to see things that are moving on the sky, that are changing. Millions of things will be changing on the sky. How do we interpret all that data? Gaia is going to have its first data release this year. So that concert last night was amazing, right? I mean, incredible. And yes, absolutely, right? And yeah. And you got to see the power of planetarium software. So that was live flying through some cutting-edge planetarium software, the UniView software. And we flew through the stars and the galaxies. We know the positions of about 100,000 stars. Gaia is very interesting because we'll know the position of 1 million stars, 3D positions, of 1 billion stars, excuse me. 1 billion's a really interesting number. 1 billion is where things become hard. 1 billion is where we can no longer just solve problems by buying better and better technology, by buying better and better graphics cards. 1 billion is where you have to start being smart. So Gaia is really telling us that we can still visualize data in real time and fly through during a concert, but we're going to have to start being smart about it. They've been at it, the big data era in many ways has already been here. It's been here in the computational community for decades. This is an image of the dark sky simulation, and like in the back, you probably can't even see all that structure, right? It's just a little tiny pattern, but each one of those little tiny filaments you can't resolve is a supercluster of galaxies. So this is simulating almost the entire Hubble volume, almost the entire universe, a trillion particle simulation. But what's really interesting to me about this project is that they're starting to think about how to be smart with the data. And in particular, as we enter the big data era, scientific visualization is going to become more and more important. In many ways in the past, and I certainly know this, many astronomers have been suspicious of visualization as an enterprise. It's pretty pictures for the public, are all well and good, but it doesn't tell you anything, right? We have a real bias towards numbers. We want to do a statistical calculation. As we enter the big data era, visualization is going to become more and more important. And the reason is simple. It scales better than statistics. The statistics we use to calculate things, to tell us about what that shape of the galaxies are, they start to fail as we get to larger and larger numbers. But actually, if we're smart about it, visualization scales very well. All we need to know to look at something is we only need the information to paint a picture on the screen. And that's just limited by the number of pixels we have. So if we're smart enough about how we access, how we pull back, how we aggregate data, we can visualize arbitrarily large data sets in real time. We just have to be very smart. Here's an example of being smart. So one of the things they did with this dark sky simulation is they were thinking about how to store the data on disk. So the data is stored on disk according to this space-filling curve, which is being demonstrated here. And that allows you just to go, right? I'm not taking a data set and bringing it to myself now. That exists on the cloud. It exists at supercomputer facilities. I just ask for what I want, what I need to visualize the data. And I can do that. So this is cute, right? But here's an example of what they're able to do with that. So this is a little web app. You can, those of you with the laptops, you can go search on it. If you have a Google Cardboard, you can even plug it in and look at it in VR. And what it's doing is it's taking a piece of this trillion particle simulation and it's visualizing it in real time, in 3D, in your web browser. But behind the scenes, what it's doing is really amazing. And I encourage you to try this out. There is a single file, a 32 terabyte file. Right? I mean, has anybody ever dealt with a 32 terabyte file? It's crazy. And you put in that number there, right at the corner, you say, I want Halo number 7,532,643. It'll get that number out of the catalog and then pull it back almost instantly. It's amazing. All right, so this is what we can do. We just need to take the data we need to draw our picture. We need the stuff close to us. We don't care as much about the stuff far away. We can group things together when they're hard to see. And we can visualize arbitrarily large data. So we're getting to the point where Visualization will solve our problems, but only if we solve the visualization problems first. We've been at that era for a while with 2D images, right? So this idea of being really smart with images. So I'm going to show you a rendering using the Worldwide Telescope, which I'll talk about in a little bit. If you looked up at the corner, we started with that vertical field of view being 60 degrees across. I've now zoomed into an area of the sky that's about 1 degree across. Through the course of this video, I'm going to zoom in by a factor of 1 million in angular scale. So if you want to think about solid angle, that's zooming in by a factor of 1 million times 1 million, 1 trillion, okay? This is why the sky is big. All right, so this is the Hubble image. Now we're looking at 1 arc minute across, but I'm going to zoom in further to this protoplanetary disk in HL tau, and this ALMA image is about an arc second across. And we're not even done yet, because we're going to zoom into an image from VLA, which shows this little clump of dust that's about 3 Earth masses. That clump of dust is a tenth of an arc second across, 2/10 of an arc second across. So from 60 to 2/10 of an arc second is about a factor of 1 million. Right. So there's your clump of dust right there. That's pretty amazing. Yeah, that's cool. Like, yeah, isn't our universe amazing, right? I mean, it's because you think about it, it's like the sky. I mean, why aren't we done with astronomy? There's just one sky, right? Observe the whole thing and be done with it. This tells people why it's hard, right? You get this impression. The sky is big. So that shows how we can solve the problem. In fact, we've done that with 2D images. We just need to do that with 3D data in the same way. And I rendered out a movie of that, but the fact of the matter is you can put together that video entirely in Worldwide Telescope. It took me about half an hour or less, and it plays in real time. Right? You just grab the pictures and you go. As we get more and more data, there's just not the technical back-end side of how we show that data. We have to start being smarter about how we display the data as well. And in many ways, this is a field that hasn't been very rigorously explored. Right? And everybody does this. Everybody visualizes data. We make plots. And how do you make a plot? Well, you take the data, you make some type of graphic, and you keep changing it until you think it looks good, and then you stop, right? But we don't know what that criteria is for what works and what doesn't work. One of the first papers to really explore this, this Cleveland and McGill paper, started to look at issues of perception, and that idea between what we visualize and how we perceive is very important. So this just kind of shows some very early results. Many are very intuitive, but if we look at basic quantities, we're able to read some quantities off of a graph more accurately than others. And this shows that hierarchy. So if we go from the left to the right, we're able to perceive these quantities more accurately and then less accurately. So those pluses represent position. We can identify position, relative position very well. Things like relative length, angle, and direction. Less well, but still pretty good. Area, we're not as good at doing area as we are at doing length. So area is less accurately perceived. Volume and curvature, even less accurately. And then things color. And here they tested saturation and shading, but I think this applies to almost all issues with color. We're really actually quite poor at distinguishing accurately color. And of course, as many of you know, some more accurately than others. Color brings up a whole host of issues. What is this map? This is the microwave background. It's the W map of the microwave background. And even if, I bet, obviously I showed the whole thing, you all know it. I bet if I cut out a little piece, you would know what it is as well. And you know what it is? Because of those colors, right? These colors have become identified with what the CMB is. And it was a terrible choice of colors. So, like, what's green? Why is there green, right? I mean, what is this trying to represent? So, when Planck went and did it, they made a better choice. So if we think about what we're trying to visualize with the CMB, is we have this uniform background, right? Very smooth, and we have deviations from a median, hotter areas and cooler areas. And what you want is a diverging color map. So here we have a white in the middle, and we go from red to blue, right? It makes sense. So, all right, whatever, you visualization guys are kind of picky. You don't like terms like false color, right? Well, but does it really matter? I mean, is this map, really that much worse than this map? I mean, color maps aren't going to kill anyone, right? Right? No, they actually kill people. So, this is actually a terrifying study. So this Michelle Borkin study in 2011, and they were looking at medical imaging data. And in particular, they were looking for weak areas in the coronary artery. And so what they had is they had imaging data on the surface of the artery. So you have this three-dimensional structure, and then you have a color map on top of that. The software previously had been using that rainbow color map that visualization people hate, but scientists seem to love. And again, like, why do you hate rainbows? Do you hate puppies and unicorns too? And there's a good reason to hate rainbows. So they made two changes. One was using actually a color map not too dissimilar to the one we just showed with Planck, the one you see in that middle panel there. And the other was, their other intervention was going from that representation of being a spatial 3D representation to a flat mapping that unwraps that surface. Both of these changes had an effect on how accurately they identified these early stressed regions. Combining them both went from an accuracy of 62%. They were only identifying 62% to 91%. So actually lots of people are being killed, probably still, by bad color maps. And there are good reasons for that. All right, so color is very important, but color also has meaning, right? Is blue hot or cold, right? I'm always asking people that. What's hot, blue or cold? And actually, thankfully, I think younger people, kids are starting to say blue is hot, right? So there's this idea of what people think and what their expectations are. And in particular, we came across that issue when we were dealing with dark matter. So we did a sky show called The Searcher a few years ago, and we had this really amazing simulation that was part of this sky show. It was what's called a constrained simulation, so it was actually trying to reproduce the current structure of the universe. And in the show, we actually represented it as the dark matter being blue on a black background. That was kind of typical. But we started to play with different representations. In particular, because we had a young graduate student at the time, Zoe Buck, who was studying how people learn about cosmology. And she was talking to people coming out of our show. And despite the fact we were clearly explaining that, the stuff that was coming together was dark matter, nobody really could identify where the dark matter was. They thought the dark matter was in the voids. It was in the area in between the matter, because dark matter should be dark. So we started to play with different representations like this. I'm kind of taxing this computer with some of these videos. I apologize. And here we're seeing a couple of different transfer functions. But in a little bit, we'll start to bring in that blue color that we used in the show. So, and this is quite striking. So she went on to actually do an online study about this. And Even when people are being told, very, very clearly being told what is what, they still make assumptions based on what they're seeing. And I know you can't read the stuff on the right, but the results are, the way we were showing it, people would answer the questions wrong. And they would answer the questions wrong, actually, more wrong than if they just randomly guessed, right? So, incredibly wrong, 20% right or something. And you went to essentially 80% right or something. So an incredible change, just by coloring things differently. So there are two sides to this. There are perceptual things we need to be smart about, but there are also educational biases we need to deal with. All right. So let's talk about display technology. You saw my lab. I like to play with toys. There you see me with Google Glass. For about a month of my life, I thought that it was a good idea to wear a beard. That was about the same month that people thought Google Glass was a good idea. But there's a new range of technologies becoming very popular now. Thank you. In particular, recently I got to play with creating an experience for the Oculus Rift for Fermilab, and that's actually the Secretary of Energy of the United States, looking at LSSD and dark energy survey data in the Oculus Rift, which is pretty awesome. What I'm really actually excited about is some of the augmented reality technology coming out. So this is Microsoft HoloLens. There's another piece called Magic Leap. And this is the ability to embed digital objects into the real world. I think for someone who works in the museum field, this is the truly transformative technology. And what people want is actually space things. So their development team had an online survey to make an app, and the first thing they made is something called Galaxy Explorer. We in the planetarium community have been dealing with immersive technology for a long time, for decades, before everyone else. So this is my institution, the Adler Planetarium, when it opened in 1930. And the language that we use to communicate has always been outside of the frame of film or a screen. And I think we have a lot that we can teach Hollywood and the rest of the creative world who's now moving into this immersive space. So planetaria have evolved. This is a screenshot from our new sky show, which premiered last night, called Planet 9. And we've gone from just representing the stars, this 2D representation of the sky, to having a 3D model of the universe that we can fly through, like we saw during the concert last night. I showed you some worldwide telescope stuff before. We can do that in the planetarium as well. And worldwide telescope in the planetarium is truly a transformative vehicle. It essentially, if I think about it as a new mode of using the planetarium. So we had the first wave of planetaria, where we could look at the 2D night sky representation. The second wave of planetaria, where we build a 3D model of the universe and we can fly through it. This third wave gives us access to all the astronomical imagery. So we can layer together, mix astronomical imagery, and if we do things right, we can have that available as soon as it's processed, and we can, because we're accessing things from the cloud and many different sources, we can essentially have access to all of the world's astronomical information in all of our planetaria. So as an example, I produced the first sky show that just runs back in Worldwide Telescope. And to give you a sense, I mentioned an earlier sky show, but this one we produced in less than 5% of the budget of a traditional planetarium show. We produced it in less than 20% of the time. There's this feeling in the planetarium community that you need to have a lot of money and be New York or Chicago to produce high quality shows. And that's true with using traditional computer graphics, Hollywood techniques. But this show, we did in a fraction of a time, not because we couldn't afford it, because it did something interesting. that we couldn't do otherwise. It's more successful than our shows produced using traditional techniques. We've been running it for 3 years, several times a day. It's a new way forward for the community, one that I think can be more inclusive of more places around the world doing cutting-edge science in their domes. It also allows you to be creative, so here's a little nod to tomorrow's keynote speaker, and we got creative with one of our adult, we have an adult evening with alcohol, and this is part of a Sky show based on Amanda's blog theme called Dirty Space News. Is anyone familiar? All right, let's encourage Amanda to talk more about Dirty Space News tomorrow. And you guys can guess what that is. It's the best picture I could find. There were some really good pictures from that show. Unfortunately, I didn't have them all with me. We're also getting a better and better understanding of how these spaces work. Those of us who work in the community, we know that these spaces work because people come up to us all the time. Scientists come up to us and tell us how they were inspired by what they saw as a child in the planetarium, and many of us were as well, so we remember that these things work, they're memorable, but we're beginning to understand why they work, and I encourage you all to go on day 5 to Kachin Yu's talk, which is really starting to really establish a formal basis for how and why these spaces are effective. All right, single talk. We spent about 6 months working on it. You see we had fun with some of the things on here, so I don't know if you can read that, but they say things like dark matter mousse and quark soup can and dark energy bicycling, right? So custom content to tell a story. If you're familiar with Michael Turner's presentations, and I remember like as a graduate student seeing him, and back when everybody just had hand-drawn black and white transparencies, his like beautiful, colorful slides were like so awesome. So we want to take what he had drawn, but bring that into a 3D immersive space. So this is showing the states of the early universe, and we turned that into a 3D model that we could fly through in Uniview, like you saw last night. So we're flying back through what we are calling the yellow brick road, which is tracing the history of the universe through quark soup, 100th of a second into the birth of the universe. There's nucleosynthesis, the creation of protons and neutrons. 3 minutes into the universe. Oh no, sorry, baryogenesis at 100th of a second, nucleosynthesis at 3 minutes, creation of the light nuclei. 300 and some thousand years in, we have atoms, and the cosmic microwave background light starts coming to us with those photons there. A few 100 million years into the universe, the first stars light up. A billion or so years in, we start to get into the realm of galaxies. So this is a 3D space. We created it from his artwork. That's the way Michael draws stars. That's the way Michael draws galaxies. And here's another lecture to show you a somewhat complex idea. This was with Michael Brown, who had given the lecture the year before. This is trying to represent the fact that this weird trans-Neptunian object called Haumea originated in a collision. And so what you're seeing is this three-dimensional orbit space, and the little white circles are things which have icy spectra, and they're kind of grouped together. And when he gave me this thought, I'm like, well, we can't do this in the planetarium. I mean, what can we do? But we can start to look at things spatially. So here's a little video that's trying to show how this is organized. So there are the orbits of the planets. There's the orbit of Haumea coming on in green. And this is these objects that have similar spectra to Haumea. And their orbits are not all the same. Here we see them with the rest of the 1,800 other objects in the Kuiper Belt. And they're the orbits of those 1,800 objects. And you know, the computer can calculate this in real time. So what's actually happening is a graphics shader is calculating those orbits, solving Kepler's equation for all 1,800 objects at 100 points around for in real time. But what you see is over time what happens is that precession creates lets these orbits scramble. So they kind of look the same, right? They got about the same tilt. They're all kind of tilted. They're all at about the same distance from the sun, but they don't look exactly the same as Haumea because they've scrambled due to precession over billions of years. But we can unscramble them in our computer and deprocess them. Which we're doing here. And now you see a relatively tight bundle of orbits all sort of grouped around the current orbit of Haumea. So this is kind of the idea of how we can take a pretty complex scientific argument, that three-dimensional plot with three different colors on it, and turn it into a simple visual argument, and one that I think is much more powerful. So the Michael Turner lecture, it doesn't make sense for the Kavli Foundation to pay us to spend 6 months creating content for a lecture. But what does make sense is if that lecture can reach more and more people. And we'll be using this technology of dome casting. So we simulcast what's happening. Sally talked about that actually yesterday. If we can simulcast what's happening in our planetarium to other planetaria around the world, we have this multiplicative effect. So all of these institutions participated in our Domecast last month. We're going to do it again because we did it in the evening as an evening event in the US, and we have to deal with time zone things. But we're going to do it at the end of July 31st, during the afternoon in the United States, so we can reach Europe as well, and hopefully get another dozen sites on board. And what I really hope is that we also have language barriers, but we get guys like this guy to translate, and hopefully we can bring that to more nations as well. So, that program involves taking some of the world's best science communicators, but improving what they're doing visually to enhance. You know, these guys are great, Michael Turner and Michael Brown, and if you put them in a dark room and they tell you a story, it's fantastic. But we can enhance it visually, we can improve the story. But what can we do with other scientists? So this is my lab again, and what we're doing in this space is we're inviting scientists in every day to have informal discussions with the public. And they can use the display devices there. I have another one there to tell a story. So this is showing when we were talking about there was a supernova discovered in M82, and we're showing like that's M82 on this tile display. There's a 3D video of a supernova detonation. There's a 3D video showing the double degenerate scenario for type 1a supernova. There's another one on the wall showing the other scenario. This is a sign-up sheet for the presenters in this program. So all of those people on that list are working scientists who come in and present in astronomy conversations. They're between 60 and 70 people, at least 2 presentations a day, every day. So the scale of this is pretty incredible. And what we're trying to do is improve how people communicate. And if you saw that list, most of those people are young, early career astronomers, postdocs, graduate students. So this guy has been very influential to me in my thinking about how to communicate science. And I think many of you know that Alan Alda now runs the Center for Communicating Science. And they do these incredible workshops. And many of those principles we're bringing to our work. They show things like this. The way we tell a story as a scientist is kind of almost backwards to the way you tell a story to the public. With the public, you got to tell them what you're interested in first. You don't bury the lead. And then you got to convince them that they're interested. Then you give them the details. You don't start with a long story about the background. We're trying to do the same thing with those astronomy conversations that we're doing with the lectures. So this is an idea that you can find on GitHub for a new platform that I want to build in the lab now, which is going to be an open source platform that allows us to take what we're doing in Chicago, but to bring it to more places around the world. One of the key technologies will be the Sage-2 interface, where we can synchronize what's happening on our wall and a wall in another science center. I'll be very fast. So here's the story. This is what I'm trying to accomplish, and I hope some of you are interested in joining me in this quest. But we want to engage scientists, and more effectively in direct person-to-person communication. And we make it more effective by creating data-rich visualizations, by using these immersive display environments, and by giving basic training in science communication. That's great. We do that. We have an impact in a city, but I'd like to have a larger impact so we can simulcast these sessions to museums and planetaria around the world using technology like the dome casting, using technology like this wall casting that I was talking about. That's a multiplicative effect. We can go farther in the future if we tap into these VR headsets like the Oculus, like the Microsoft HoloLens, and we bring these experiences we created from the museums into people's homes, and then we can have an exponential effect. So thank you very much. Here's my contact information. I've got stuff up on GitHub if you want to check out some of this stuff. And I would love to earn some new collaborators out of this talk, and please feel free to email me. Thank you guys very, very much.
Thank you very much, Mark. Are there any questions for Mark? Okay, here in the front we have two.
Thank you, Mark. That was really very interesting. And I wonder if you have any thoughts on whether these technologies might be of greater value to the scientists themselves or to the public, or do you think that it's essentially equal positive impact for both communities?
Yeah, so I think part of that story is, in many ways, I was telling my background. I kind of bristle at that division between being a scientist and outreach person. So I think the power with these tools is that they work for both. When I was working on Sloan, I could fly around the planetarium, and there were hundreds of other people who'd worked on this survey. And many of them studying the statistics of large-scale structure, they had no idea what the survey actually looked like. I think scientists dramatically underestimate the power of visualization. I think nobody realizes what's capable in the modern digital planetarium. That's something we're trying to correct. So when we bring scientists into this, part of the story is we're going to help you explore your data better. All those scientists who are coming in to give talks, it's not just for outreach. We help them make better tools, many of which have led to them better understanding what they're working on. So I think it's a two-way street.
Hello. In terms of cosmological simulations, I remember talking to the people who worked on the Bolshoi simulation and the Millennium and the Virgo. What's the next step in this, and who else is in the forefront of the simulations as of now?
Well, that's a good question. I don't know if I can exactly answer it, but some of these modern simulations that are coming, like Aquarius or Illustrious, or some of the work that's being done at Argonne National Lab, the resolution and the scale of them are getting bigger and bigger. So you can both simulate the entire volume of the universe and also resolve individual galaxies forming at the same time. So it's pretty remarkable what the state of the art is right now.
Hello. I think it's really good. I think the same than you, that it's really good to visualize what you want to explain to people. But usually when I give a class, I always discover that it was something that I didn't explain. So the people doesn't get really into what I'm trying to show. So for example, dark matter. You have a very good image of where is dark matter. You have trouble with color, as you said. But how do you explain what is dark matter? How do you do that before to show the image?
Yeah, I mean, I think well, that's a deep question. It's deep in a lot of ways. I think with any kind of communication, whether it's visual or verbal, there are a couple of points there. One is that we're always going to fail, right? We're always going to fail. What we're trying to talk about is how the entire universe works, right? So like, people come in for 15 minutes, like, I'm going to tell you about the entire universe, everything we know in it, its entire history, and how it all works, right? So we always fail at what we're doing. And often what we need to do is to be very conscious of where we're willing to fail and where we want to succeed. And that changes all the time. So it may be that I don't actually care if you understand what dark matter is. I'm showing you this video that shows you how things come together in the universe. And actually, maybe I don't even care if you know if it's dark matter or not. But understanding where to fail, or where it's acceptable to fail, is a key component. That's kind of a downer to end on, but what?
Okay, let's thank Mark once again. And I would... Thank you, Mark.